What if I told you that everything you think you know about matter is wrong? That the solid chair you're sitting on, the water you drink, even the air you breathe represents less than 1% of what matter can actually become. Right now, scientists are creating forms of matter so bizarre they seem to violate the laws of physics, matter that flows upward, defying gravity. Matter where thousands of atoms suddenly forget they're individuals and become one giant quantum entity. Matter so perfectly fluid, it makes water look sticky. From the moment we open our eyes as children, we are surrounded by matter in its most familiar forms. The solid earth beneath our feet, the liquid water that quenches our thirst, the invisible gas we breathe with every moment. For thousands of years, these three states seemed to be all that reality had to offer. To the human mind, they felt complete: stone, river, and air. Everything we could touch, drink, or breathe fit neatly into these categories, and the world felt ordered, predictable, and whole. But here's what will blow your mind. Hidden beneath this surface simplicity, the universe carried secrets that would only be revealed with patience, curiosity, and an ever-deepening desire to understand. Humanity has always asked questions. What is the world made of? How do its pieces fit together? And why does it behave the way it does? Long before the first microscopes, before the idea of atoms, people looked at matter and tried to reduce it to its essence. Ancient philosophers in Greece, India, and China imagined that everything could be traced back to elemental forces: earth, water, fire, air. These ideas were not experiments, but visions, attempts to see the invisible through logic and intuition. But wait, there's more. The Greek philosopher Democritus went further. He imagined that if you kept cutting matter into smaller and smaller pieces, eventually you would reach a limit, an indivisible building block. He called it the atom, from the word meaning uncuttable. He could not prove it, but he believed the universe must have such a foundation. For 2,000 years, this idea rested like a seed waiting for the right season, until science found tools sharp enough to test it. When microscopes came, they showed us that matter was not continuous, but built from tiny grains, just as Democritus had dreamed. Chemistry revealed that each element had its own type of atom, and physics uncovered that atoms themselves were made of still smaller parts: protons, neutrons, electrons. The familiar world was no longer built from 4 elements, but from an entire alphabet of matter, arranged in the periodic table, each symbol standing for a different kind of atom. For a long time, even as we uncovered the atom, the picture of matter still seemed simple. Atoms could arrange into solids, where they locked together in rigid forms. They could move more freely in liquids, flowing and reshaping endlessly, or they could spread out as gases, filling the space available. That was the tidy picture, one that comforted the human mind, and yet nature does not obey our desire for simplicity. Slowly, through experiment, new states began to appear. The first was plasma. When gases are heated or energized enough, they can become stripped of their electrons, turning into a sea of charged particles. This was no longer just gas, but something new, glowing and alive, like the sun itself. Plasma revealed that matter could transform in ways that went beyond our intuition. And if plasma could exist, what else was possible? Here's where things get really wild. By the 20th century, physics had begun to ask stranger questions. What happens if matter is pushed to extremes not found in daily life? What happens if it is heated to unimaginable temperatures or cooled to fractions of a degree above absolute zero? Could matter organize itself in entirely new ways? The answers, it turned out, would take us into realms that would have felt like science fiction if they had not been measured in the laboratory. To understand these exotic states, we need to step back and consider the world not just as a collection of particles, but as a place where waves and particles blur. In our daily lives, an apple is an apple, a stone is a stone. But at the smallest scales, atoms behave like both particles and waves. They have a duality that resists intuition. This dual nature is the heart of quantum mechanics, and it is this strange property that allows matter to assemble into forms beyond the solid, the liquid, the gas, and the plasma. Picture this scenario. Imagine a crowd of people dancing, each moving in their own rhythm. Normally, their steps are uncoordinated, overlapping, sometimes colliding. But what if, in some unusual condition, every single person began to move in perfect synchrony, every footfall aligning as if they were one being? This is what happens when atoms are cooled close to absolute zero. Their individual quantum waves stretch and overlap until they lose their individuality. Instead of many, there is one, a collective state that moves together, a kind of superatom. This is the Bose-Einstein condensate, predicted by Albert Einstein and Satyendra Nath Bose in the 1920s, but only created in the laboratory 70 years later, when technology allowed atoms to be cooled and trapped with lasers and magnetic fields. The story of this discovery is not just scientific but human. Einstein and Bose worked with pencil and paper, guided by equations and imagination. They foresaw that particles, if cooled enough, would fall into a single quantum state, but at that time there was no way to test it. Their prediction waited, like a message in a bottle drifting through time, until experimentalists in the 1990s finally had the tools to cool atoms to billionths of a degree above absolute zero. When the first condensate was seen, it was a faint blur of light from trapped rubidium atoms, but it confirmed that Einstein and Bose had been right all along. And so a new state of matter joined the list, one stranger than any before. In a Bose-Einstein condensate, atoms act not as individuals, but as a single wave function, a shared identity that defies our normal categories. The familiar states of matter seemed almost provincial by comparison. Solids, liquids, gases, these were only the beginning, a tiny part of the full spectrum. Before we dive deeper into these condensates and other exotic states, it is worth reflecting on how each discovery changed not only science, but also our sense of place in the cosmos. For the ancients, the four elements explained everything. For modern science, atoms and the periodic table provided the new foundation. But with the arrival of quantum mechanics and the experimental ability to push matter to its extremes, a door opened into a hidden landscape. Suddenly, it was no longer enough to classify matter by what we saw in daily life. Matter could exist in ways that no human had ever experienced directly, states found only in the hearts of stars in the first seconds after the Big Bang, or in laboratories cooled with lasers and magnetic fields. The beauty of this journey is that it reveals how limited our intuition really is. We live our lives between 0 and 100 degrees Celsius, surrounded by familiar conditions. But the universe itself is far larger, ranging from the searing plasma of stars at millions of degrees to the frozen dark of interstellar space, only a few degrees above absolute zero. Within that vast range, matter explores possibilities we cannot imagine until experiment brings them to light. Think for a moment about the act of cooling atoms. Each step downward in temperature is a step into strangeness. At room temperature, atoms in a gas zip about at hundreds of meters per second. Cool them with lasers and they slow, becoming sluggish, their motion nearly still. As the temperature drops toward absolute zero, their quantum nature begins to stretch out like ripples overlapping in a pond. At some point, those ripples are no longer separate. They merge, forming a single wave that encompasses them all. What we see in the laboratory is not just cold atoms, but a glimpse of the universe's hidden order, one that lies dormant in the everyday world but emerges when pushed to extremes. The same is true in the opposite direction, when matter is heated to staggering temperatures. In the early universe, moments after the Big Bang, matter was not solid, liquid, or gas, but a sea of quarks and gluons, particles free from the protons and neutrons we know today. For a brief moment, the cosmos itself was in an exotic state, one recreated in modern times only in giant particle colliders, where heavy ions smash together and melt back into that primordial soup. These are not just experiments in physics, they are time machines, windows into the infancy of everything we see. In this way, exotic states of matter are not separate curiosities, but clues to the fundamental story of the cosmos. They connect the human laboratory to the universe itself, showing that the same laws hold across scales from the smallest atom to the largest galaxy. When we study a Bose-Einstein condensate in a lab, we are also glimpsing the behavior of neutron stars. When we create a quark-gluon plasma in a collider, we are reenacting the first heartbeat of the universe. The more we learn, the more we realize how narrow our familiar window truly is. The three states we grow up with are only a sliver of possibility, a thin slice through a vast landscape. And If there are still new states to be discovered, and many physicists believe there are, then our picture of matter is not complete, but only beginning. As we move deeper into this journey, we will see that exotic matter is not only strange, but useful. Superfluids that flow without friction, superconductors that carry electricity without resistance, condensates that may one day form the basis of quantum computers. These states are not just curiosities, they are tools, perhaps even stepping stones to new technologies that will shape the future. But before we can grasp their promise, we must first understand their nature, and that begins with the simplest and yet strangest of them all, the Bose-Einstein condensate. The laboratory where Bose-Einstein condensates were first created was not unlike many others, filled with wires, lasers, vacuum chambers, and the quiet hum of machinery. Yet within this setting, something profoundly new emerged, something that had never existed on Earth before that moment. To make such a state is to wrestle with nature itself, because atoms at room temperature are restless, darting around with so much energy that they refuse to sit still. The task is to slow them down, to drain away their heat until they no longer act as individuals. This cooling requires delicacy, precision, and patience, for every fraction of a degree closer to absolute zero brings new challenges. Scientists use lasers to begin the process. At first, it may seem odd that beams of light, which we associate with energy and heat, can instead be used to cool. But light carries momentum, and by tuning lasers to just the right frequency, atoms can be made to absorb and then re-emit photons in such a way that their motion gradually slows. Imagine trying to stop a speeding car not by slamming on the brakes, but by gently bouncing ping-pong balls off its hood until it eases to a halt. That is the subtle art of laser cooling. But here's what makes this even more fascinating. Once the atoms are slowed enough, magnetic fields are brought into play. Magnetic traps hold the atoms in place like invisible hands, keeping them from escaping as they lose more energy. Bit by bit, the temperature drops until what once was a cloud of independent particles begins to change in nature. Instead of behaving like marbles colliding in a box, the atoms become waves that stretch and overlap. Then comes the moment of transition, and this is where things get truly mind-bending. At a critical temperature, which depends on the density and the type of atom used, the system shifts. Suddenly, the overlapping waves merge into a single wave function, a collective identity shared by every atom in the trap. The individual dissolves into the group, and what had been many becomes one. This is not a metaphor, but a measurable reality. The atoms lose their individuality, and the entire cloud behaves as though it were a single particle. Scientists watching this transition describe it with a sense of awe. Atoms that were once an invisible gas now emit a faint glow, their distribution changing, their properties unlike anything seen before. The equations of Bose and Einstein, once only marks on paper, come alive in the laboratory. For a physicist, this is a kind of alchemy, the creation of a new form of matter conjured from the extreme edge of possibility. What makes Bose-Einstein condensates so fascinating is not just their existence, but their behavior. In this state, matter becomes a kind of superfluid, flowing without resistance. If you were to stir it, vortices would appear, tiny whirlpools that form in patterns dictated not by chance, but by quantum rules. These vortices arrange themselves in perfect lattices, as though the fluid were a crystal of motion, geometry, written into the flow. Another property is coherence. Normally, atoms scatter light randomly, like raindrops diffusing a beam of headlights. But in a condensate, the atoms act together, amplifying and reinforcing each other so that light passing through can reveal patterns of interference as though the entire cloud were one giant atom. This coherence is the same principle behind lasers, but in a condensate, it appears not as a device built by humans, but as a property of matter itself, unlocked by cooling and patience. These behaviors are not only strange, but useful. Because condensates act as giant quantum objects, they can be used to probe fundamental questions about the universe. For instance, scientists use them to simulate conditions that might occur in black holes, or to study the behavior of matter in the early universe. They are a laboratory window into conditions otherwise impossible to reach. And yet, there is something deeply poetic about their fragility. Bose-Einstein condensates exist only under the most delicate conditions. A touch of heat, a stray vibration, even the smallest disturbance can destroy them, scattering the atoms back into individuality. They are like snowflakes in a furnace, fleeting, delicate, vanishing almost as soon as they appear. But within their brief existence, they reveal truths about nature that endure far longer. To appreciate the strangeness of a condensate, consider how it changes our idea of identity. We are used to thinking of the world as made of separate parts, atoms, people, planets. Each has its own boundary, its own independence. But in a condensate, those boundaries blur, the many dissolve into one, and individuality ceases to matter. For a moment, the atoms remember that they are not separate at all, but expressions of a deeper unity. This challenges not only our physics, but also our philosophy, for it suggests that separateness is only a condition, not a truth. Experiments with condensates have shown other remarkable effects that will absolutely amaze you. For example, sound can travel through them in unusual ways, revealing quantum versions of shock waves. Light can be slowed almost to a stop as it passes through a condensate, something unimaginable in ordinary matter. In one experiment, scientists managed to store light within a condensate and then release it, as though matter itself had become a memory bank for photons. Such experiments blur the line between energy and matter, between particle and wave, between what we know and what remains a mystery. The ability to slow light to a crawl represents one of the most striking demonstrations of how condensates can manipulate the fundamental properties of nature. When light enters a Bose-Einstein condensate under the right conditions, the collective behavior of the atoms creates what physicists call electromagnetically induced transparency. The condensate becomes almost perfectly transparent to certain frequencies of light, but paradoxically, this transparency comes with a price. The light slows down dramatically from its usual speed of 300 million meters per second to less than the speed of a bicycle. But the truly mind-blowing part comes next. By carefully adjusting the properties of the condensate, scientists can bring light to a complete stop. The photons don't disappear. Instead, their energy and information are stored in the quantum state of the atoms. Later, by changing the conditions again, the light can be released, continuing its journey as if nothing had happened. It's like pressing a pause button on light itself. This slow light phenomenon has profound implications for quantum information processing. Imagine being able to capture a beam of light carrying quantum information, hold it in matter for as long as needed, and then release it on command. This could form the basis of quantum memory devices, essential components for future quantum computers and communication networks. The condensate becomes a translator between the language of light, which carries information efficiently over long distances, and the language of matter, which can store and process that information. Condensates also allow us to study phenomena that happen in the vastness of space, but in miniature. Certain configurations of a Bose-Einstein condensate can mimic the behavior of event horizons in black holes, allowing scientists to study Hawking radiation, a theoretical process by which black holes emit particles. In this way, the fragile, chilled atoms in a lab on Earth can echo the titanic forces of collapsing stars. This connection between the smallest and the largest, between the delicate and the cosmic, is part of what makes exotic states so compelling. These analog black holes work by creating a region in the condensate where the flow speed exceeds the speed of sound. Just as nothing can escape from beyond a black hole's event horizon, sound waves cannot propagate against the flow in these supersonic regions. The boundary between the subsonic and supersonic regions acts like an event horizon, and the condensate naturally produces pairs of sound waves that separate, with one trapped in the supersonic region and the other escaping to the subsonic side. This mimics the Hawking radiation process, where particle pairs are created near a black hole's event horizon, with one particle falling in while the other escapes. The beauty of these experiments is that they allow us to test one of the most bizarre predictions of physics in a controlled laboratory setting. Hawking radiation has never been directly observed from real black holes because it's incredibly weak and difficult to detect against the cosmic background. But in condensates, the analogous process is amplified and can be measured with precision instruments. These studies have confirmed key aspects of Hawking's theory and revealed new insights into the quantum nature of space-time itself. It is worth remembering that the existence of Bose-Einstein condensates is not obvious. Without quantum mechanics, without the strange principle that particles can behave like waves, such a state would make no sense. In the classical world, particles are separate, always distinct. Only in the quantum world can individuality dissolve, only in the quantum world can many become one. This shows us again how limited our daily intuition is and how much of reality lies hidden behind the curtain of the quantum. There is also a certain humility in these discoveries. For centuries we thought we understood matter, solid, liquid, gas. Even when plasma was added, it seemed like a rare exception. But condensates remind us that our knowledge is provisional, always open to revision. There may be states of matter still undiscovered, waiting in the extremes of temperature or pressure in the uncharted corners of the cosmos. The universe does not care about our categories. It reveals itself only when we ask with patience and with tools sharp enough to see. The creation of Bose-Einstein condensates was a milestone, but it was also a beginning. Once physicists realized that such a state was possible, they began to search for other, related states. Could fermions, particles that resist occupying the same quantum state, also form condensates? Could other exotic behaviors be unlocked at extremes of cold or heat? Each question opened new doors, and the answers began to multiply. Before moving to those other states, pause to consider what has already been revealed. The simple act of cooling atoms, of slowing their frantic motion until they merge into unity, has shown us that matter is not fixed but fluid, not limited but expansive. Solids and liquids may dominate our senses, but beyond them lies a spectrum of possibilities, each stranger than the last. In condensates we see matter become wave, unity emerge from multiplicity, and the boundaries we thought were solid dissolve into something deeper. As these discoveries sink in, it becomes clear that we are not just cataloguing states of matter, we are expanding our concept of reality itself. What once seemed impossible, atoms acting as one, light brought to a halt, miniature echoes of black holes appearing in a lab, is now part of our understanding. And if the universe can reveal such wonders here, in the fragile experiments of human hands, what greater marvels might it conceal in the depths of stars, in the first seconds of creation, or in the quantum fabric that underlies all things? Now, here's where the plot thickens. When physicists first created Bose-Einstein condensates, it was natural to ask whether all particles could do the same. After all, if bosons could merge into a shared quantum state, why not fermions? But here, the rules of nature draw a sharp line. Fermions, which include electrons, protons, and neutrons, are bound by the Pauli exclusion principle. No two fermions can occupy the same quantum state. This is why matter has structure, why electrons fill orbitals in atoms instead of collapsing into one lowest energy level. It is why the world is solid, why atoms do not simply slide into one another. Without this principle, everything would smear into sameness, but with it, individuality is enforced, so the challenge was clear. Could a state be found where fermions, normally so resistant to sharing, could in some way come together? The answer came not from treating fermions as individuals, but from pairing them. Under the right conditions, two fermions can bind together into a composite particle, and this composite behaves like a boson. Once paired, they are no longer locked by exclusion in the same way, but freed to join the collective. This principle was already known in superconductors, where electrons form what are called Cooper pairs. These pairs move through a lattice without resistance, gliding effortlessly as though friction no longer exists. Inspired by this, researchers cooled fermionic atoms and encouraged them to pair, and in 2003, the first fermionic condensate was created. It was a cousin to the Bose-Einstein condensate, similar yet distinct, another demonstration that nature's possibilities are wider than we imagine. But the formation of Cooper pairs in superconductors reveals an even deeper truth about quantum mechanics. These pairs don't exist in isolation, they emerge from a complex dance of all the electrons in the material. When one electron moves through a metal, it slightly distorts the lattice of positive ions, creating a region of excess positive charge. This distortion travels through the material like a wave, and another electron can be attracted to this region of positive charge. In normal circumstances, the mutual repulsion of the electrons would prevent any lasting attraction. But at low temperatures, where thermal vibrations are suppressed, this indirect attraction through the lattice can overcome the electrical repulsion, allowing electrons to form pairs. What makes Cooper pairs truly remarkable is their size. These pairs don't consist of electrons that are close together in space. Instead, they can be separated by hundreds of other electrons while still maintaining their paired quantum state. It's as if two dancers in a crowded ballroom maintain perfect coordination even when separated by dozens of other people. The pair exists not as a local bond, but as a correlation that spans the entire material, a ghostly connection maintained by quantum entanglement. Fermionic condensates show us that the universe's rules are not obstacles but invitations. Even principles that seem like barriers, such as the exclusion rule, can become stepping stones to new states of matter if approached creatively. Matter does not simply resist, it responds to the conditions we create. And with patience, it reveals new forms of order. The transition from individual fermions to a fermionic condensate represents one of the most profound phase transitions in nature. Unlike the smooth transition that occurs in Bose, Einstein condensates, fermionic systems can undergo what physicists call a BCS-BEC crossover. On one side of this transition, you have weakly paired fermions forming a superconducting state similar to what happens in metals. On the other side, you have tightly bound pairs that behave like bosonic molecules and can form their own Bose, Einstein condensate. But the truly fascinating regime lies in between, in the crossover region, where the pairing is neither weak nor strong, but something entirely new. Here, the system exhibits properties that don't fit neatly into either category. The pairs are neither loosely correlated electrons nor tightly bound molecules, but something in between, a new kind of quantum matter that bridges two different physical regimes. This crossover has no analogue in conventional superconductors, making fermionic atoms in optical traps unique laboratories for exploring this exotic territory. Scientists have discovered that this crossover region exhibits what they call unitary behavior, where the interactions between particles are as strong as quantum mechanics allows while still remaining well-defined. In this regime, the system becomes scale invariant, meaning it looks the same at all length scales. This property makes it a perfect laboratory for testing fundamental theories about strongly interacting quantum systems. To move deeper into this realm, consider helium, one of the simplest and most abundant elements in the universe. Helium is familiar to us as the gas that fills balloons, light enough to float. But when cooled, helium takes on behaviors that seem to defy reason. At temperatures near absolute zero, liquid helium becomes a superfluid. This is not simply a very cold liquid, but something entirely new. A superfluid flows without viscosity. If placed in a container, it will climb the walls, spilling over the edge as though gravity were a mere suggestion. It can pass through pores so fine that no ordinary liquid could squeeze through, moving like a ghostly tide. Are you ready for what comes next? Superfluid helium astonishes anyone who sees it. Place a rotating container of the fluid on a table, and the liquid inside does not spin in the ordinary way. Instead, it forms quantized vortices, tiny whirlpools that mark the places where the fluid's quantum nature asserts itself. These vortices arrange into patterns like a constellation written in liquid motion, visible evidence that the superfluid is not obeying classical rules, but quantum ones. This strange flow has no counterpart in our everyday experience. Imagine stirring a cup of tea, only to watch the liquid continue swirling forever, never slowing, never stopping. That is the superfluid reality. No energy is lost, no friction saps the motion. It is as though the liquid has become a pure expression of movement itself, unburdened by the resistances that govern the ordinary world. The discovery of superfluid helium in the 1930s opened a new chapter in physics. It was a tangible, visible demonstration that quantum mechanics could reach up from the microscopic world into our macroscopic lives. Here was a liquid you could see with your eyes, touch with your hands, yet its behavior was dictated by quantum laws normally hidden from view. This is part of what makes exotic states so captivating. They reveal that the rules of the very small can manifest in the realm of the very large, reshaping our sense of what is possible. But superfluid helium comes in two varieties, each with its own personality. Helium-4, the more common isotope, becomes superfluid at 217 Kelvin through Bose-Einstein condensation of the helium atoms. But helium-3, with one fewer neutron, is a fermion and cannot undergo the same transition. Instead, at the incredibly low temperature of just 2 mil-Kelvin, 0.002 of a degree above absolute zero, helium-3 undergoes its own transformation into superfluidity through the formation of Cooper pairs, just like electrons in superconductors. The superfluidity of helium-3 is even stranger than that of helium-4. The Cooper pairs in superfluid helium-3 have internal structure. They can have angular momentum and can point in different directions. This creates a rich landscape of possible phases, each with its own unique properties. Some phases have spontaneous magnetism, others break time reversal symmetry, and still others exhibit topological order that could be useful for quantum computing. These different phases of helium-3 provide a window into some of the most exotic physics imaginable. In one phase, the pairs have orbital angular momentum, creating a state analogous to what might exist in the cores of neutron stars. In another phase, the pairs spontaneously choose a preferred direction in space, breaking rotational symmetry and creating textures and defects that behave like cosmic strings in miniature. These topological defects can't be removed by smooth deformations. They're protected by the fundamental topology of the quantum state itself. Superfluids also reveal another truth about nature, that order and coherence can emerge spontaneously. Atoms cooled into alignment act as though they are aware of one another, as though they have chosen unity over separation. Of course, no choice is involved. It is the inevitable outcome of quantum laws at extreme conditions. But to the human observer, it carries the flavor of cooperation, of individuality melting into harmony. The superfluid state also exhibits some of the most precise measurements possible in physics. Persistent currents in superfluid loops can be measured to extraordinary accuracy, allowing scientists to test fundamental physics with unprecedented precision. These currents can flow in perfect circles for months or even years without any measurable decay, creating natural laboratories for studying quantum mechanics on macroscopic scales. One of the most striking demonstrations of superfluidity is the fountain effect. When superfluid helium is heated from below, it doesn't simply rise by convection like a normal fluid. Instead, it forms a jet that can shoot several feet into the air, driven entirely by the temperature gradient. This happens because the superfluid has zero entropy, it's in a perfectly ordered quantum state, so when heat is added, the normal component of the fluid, yes, superfluids have both superfluid and normal components, rushes toward the heat source while the superfluid component fountains away. The two-fluid model of superfluids represents one of the most successful theories in condensed matter physics. According to this model, superfluid helium behaves as if it were two fluids occupying the same space, a superfluid component that flows without friction and carries no entropy, and a normal fluid component that behaves more conventionally. The relative amounts of these two components change with temperature, with the superfluid fraction approaching 100% as the temperature approaches absolute zero. From superfluids, it is only a short step to superconductors, another phenomenon that seems at first glance like magic. In an ordinary conductor, such as copper wire, electrons flow under the push of voltage, but they scatter against atoms, losing energy as heat. This is why wires warm when electricity runs through them. But in a superconductor, under the right conditions, electrons pair into Cooper pairs, and these pairs move as a coherent whole. They glide through the lattice of the material without scattering, without resistance. Electricity flows endlessly, unimpeded, as though the wire has become a perfect riverbed for current. This discovery, first made in 1911, changed the landscape of physics. Imagine a loop of superconducting wire carrying current. In principle, that current could flow forever, undiminished, for years, for centuries, for as long as the material remains in its superconducting state. Such perfection does not exist anywhere in the ordinary world, yet here it is, born of the same quantum rules that give us condensates and superfluids. But wait, it gets even better. Superconductors have practical uses as well as philosophical weight. They make possible the powerful magnets used in MRI machines, in particle accelerators, in experimental fusion reactors. They promise technologies yet to be realized, from lossless power grids to magnetic levitation trains. The dream of a future shaped by superconductivity has not yet fully arrived, for most superconductors work only at very low temperatures. But researchers continue to seek materials that can become superconducting at room temperature, a discovery that would revolutionize technology overnight. The history of superconductivity is filled with surprises. After the initial discovery in mercury, scientists found superconductivity in various metals, and for decades, the highest transition temperature, the temperature below which a material becomes superconducting, barely crept upward. The theoretical understanding developed by Bardeen, Cooper, and Schrieffer, BCS theory, explained how electron pairs could overcome their mutual repulsion and flow without resistance, but it also suggested that superconducting transition temperatures would be fundamentally limited to relatively low values. Then, in 1986, everything changed. Georg Bednorz and Alex Muller discovered superconductivity in a ceramic compound that broke all the rules. Not only was it a ceramic, a class of materials not expected to conduct electricity at all, let alone superconductor, but its transition temperature was higher than BCS theory suggested was possible. This discovery launched the era of high-temperature superconductivity and sparked a global race to find materials that could superconduct at increasingly high temperatures. The discovery of copper oxide superconductors revealed that nature had more tricks up its sleeve. These materials don't fit the conventional BCS picture. Instead of the simple S-wave pairing of conventional superconductors, they exhibit D-wave pairing, where the Cooper pairs have orbital angular momentum. The pairing mechanism itself remains mysterious, involving complex interactions between electrons, magnetism, and the crystal lattice that are still not fully understood decades after their discovery. High-temperature superconductors also exhibit rich phase diagrams with multiple competing states of matter. As you change the concentration of charge carriers or apply magnetic fields, these materials can transition between superconducting states, antiferromagnetic states, charge-ordered states, and various forms of quantum liquid states. Each transition reveals new physics, new ways that electrons can organize themselves in strongly correlated systems. There is also beauty in the mathematics of superconductivity. The paired electrons act as a collective wave function spreading through the material, immune to disruptions that would scatter individuals. The exclusion principle, that once seemed like a barrier, becomes the foundation for new coherence, for unity at a higher level. This echoes the story of fermionic condensates, where pairing unlocks a new state. Nature seems to whisper the same lesson in many forms, that cooperation leads to transformation, that unity gives rise to new properties. One of the most striking properties of superconductors is the Meissner effect, the complete expulsion of magnetic fields from the interior of the superconductor. This isn't just the absence of electrical resistance, it's active expulsion of magnetism. When a superconductor cools below its transition temperature in the presence of a magnetic field, it generates surface currents that create an exactly opposite magnetic field, cancelling out the external field inside the material. This effect allows superconductors to levitate magnets, creating the striking visual demonstrations that have made superconductivity famous. But the Meissner effect reveals something deeper about the nature of superconductivity. It shows that superconductivity is not just perfect conductivity, but a true thermodynamic phase of matter, as distinct from normal metals as liquid water is from ice. The energy gap that opens in the electronic spectrum when a material becomes superconducting represents a fundamental change in the ground state of the system, a symmetry breaking that transforms the entire electronic structure. The applications of superconductivity extend far beyond power transmission and magnetic levitation. Superconducting quantum interference devices, WIDs, SIDEs, can detect magnetic fields so weak they would be imperceptible to any other instrument. These devices can measure the magnetic fields generated by the human brain and heart, opening windows into the electrical activity of our most vital organs. They can detect the faint magnetic signatures of buried archaeological artifacts or mineral deposits deep underground. In the realm of quantum computing, superconducting circuits form the basis of some of the most advanced quantum processors. The Josephson junction, where a thin insulating barrier separates two superconductors, creates a quantum device where individual Cooper pairs can tunnel through the barrier, creating the quantum bits, qubits, that store and process quantum information. These superconducting qubits can be manipulated with exquisite precision, allowing complex quantum algorithms to be executed. But perhaps the most ambitious application of superconductivity lies in fusion energy. The ITER project, currently under construction in France, will use superconducting magnets to confine a plasma hotter than the center of the Sun. These magnets must maintain magnetic fields of unprecedented strength and precision while operating at temperatures just a few degrees above absolute zero. The contrast is staggering. Materials cooled to near absolute zero holding plasma at 100 million degrees Celsius, with the fate of clean energy hanging in the balance. Taken together, fermionic condensates, superfluids, and superconductors form a family of quantum states, each revealing a different facet of matter's hidden potential. They show us that matter is not fixed but flexible, that under the right conditions it can move in ways that defy our classical expectations. They also show us that quantum mechanics is not confined to the invisible world of atoms, but can reach upward into the scale of things we can see and touch. Imagine a thread running through all these discoveries, binding them together. At one end is the Bose-Einstein condensate, born of bosons merging into one. At the other end are fermions, refusing to merge but finding unity through pairing. Along the way are liquids that climb walls and wires that carry endless current. The thread is quantum coherence, the ability of particles to act not as separate entities but as parts of a whole. This coherence is fragile, delicate, easily broken by heat or noise. And yet, when conditions are right, it emerges with a power that transforms matter itself. For us as observers, these states are more than curiosities. They are mirrors of possibility, glimpses of what the universe can do when extremes are reached. They remind us that the world we know is only a slice, that the full spectrum of matter is richer, stranger, more varied than our senses suggest. And in that richness lies both mystery and promise. The promise is technological. Superconductors could revolutionize energy, making transmission lossless, enabling new forms of computation. Superfluids and condensates could help us simulate the universe, probe its earliest moments, and perhaps unlock new ways of controlling matter and light. Fermionic condensates may help us understand the behavior of dense matter in neutron stars, where fermions are packed together under crushing gravity. But the mystery is equally compelling. Why does nature allow such states? Why does unity emerge at extremes? What does it mean that light can be slowed, that matter can lose viscosity, that resistance can vanish? These are not only scientific questions, but philosophical ones, touching on the nature of reality itself. The journey into these states also reflects a journey into human imagination. Each discovery required not only experiments, but leaps of thought, visions that went beyond what was already known. Bose and Einstein imagined atoms merging. Physicists in Leiden cooled mercury and found superconductivity. Researchers in Moscow watched helium climb walls. Each step was an expansion of the possible, a reminder that reality is not limited to what is familiar. But if we turn the dial in the opposite direction, from the coldest extremes to the hottest, a new family of exotic states appears. These are not born of calm and unity, but of violence and heat, where atoms are torn apart and matter dissolves into its most fundamental components. To encounter these states is to travel back in time, to glimpse the universe as it was in its first trembling moments after the Big Bang. The strange journey of matter does not end with the stillness of cold condensates or the flowing perfection of superfluids. If we turn the dial in the opposite direction, from the coldest extremes to the hottest, a new family of exotic states appears. These are not born of calm and unity, but of violence and heat, where atoms are torn apart and matter dissolves into its most fundamental components. To encounter these states is to travel back in time, to glimpse the universe as it was in its first trembling moments after the Big Bang. Consider the quark-gluon plasma. In our ordinary world, protons and neutrons form the building blocks of atomic nuclei, and within them live quarks bound together by gluons, the carriers of the strong force. These quarks are never seen alone, they are confined, locked inside their prison of nucleons, bound so tightly that separation seems impossible. But if the temperature rises high enough, if the energy is intense enough, those bonds can break. The quarks are liberated, the gluons spread freely, and matter reverts to the state it held in the first microsecond of the universe's life. This plasma is unlike anything we can imagine in daily life. It is a fluid of unimaginable density, a searing ocean where quarks and gluons drift freely. It existed when the cosmos was less than a heartbeat old, when time itself was just beginning to stretch. To study it is to touch the origin of matter, to witness creation not in theory but in experiment. Physicists recreate quark-gluon plasma in enormous particle colliders, where heavy ions are smashed together at nearly the speed of light. For the briefest moment, a tiny fireball is born, hotter than the core of any star, and within it, quarks roam free. Detectors capture the faint traces of this vanished state, the particles that stream out as the plasma cools and recombines into ordinary matter. What lasts for less than a trillionth of a second is enough to confirm that we have reached back into the universe's earliest chapter. What is most remarkable is that this plasma, once thought to behave like a gas, turns out to act like a liquid, a nearly perfect liquid, flowing with less resistance than any other known substance. Its behavior defied expectations, revealing again that the universe is not bound by our assumptions but surprises us when we look closely enough. The hottest matter ever created in a lab turns out to be not chaotic but elegant, flowing with a grace that is almost paradoxical. The creation of quark-gluon plasma requires extraordinary energies. At the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory and the Large Hadron Collider, LHC, at CERN, gold or lead nuclei are accelerated to nearly the speed of light and smashed head-on. The collision creates a tiny droplet of matter with a temperature of several trillion degrees, about 250,000 times hotter than the center of the Sun. For comparison, if you could heat a grain of sand to this temperature, it would release enough energy to power a city for several minutes. In these collisions, the energy density reaches levels that haven't existed in the universe since the first few microseconds after the Big Bang. The strong force that normally confines quarks inside protons and neutrons becomes overwhelmed by the intense energy, and the barriers between individual nucleons dissolve. What emerges is a state of matter where the fundamental constituents of atomic nuclei, quarks and gluons, move freely through space for the first time since the cosmic dawn. But studying this plasma presents enormous challenges. It exists for only about 10 Newton 23 seconds before cooling and fragmenting into ordinary particles. Scientists must infer its properties from the thousands of particles that emerge from each collision, like detectives reconstructing a crime scene from scattered evidence. They look for specific signatures, the way certain particles are produced, how energy and momentum are distributed, and how the emerging particles are correlated with each other. One of the most striking discoveries is that quark-gluon plasma behaves like a nearly perfect fluid with extremely low viscosity. This was completely unexpected. Most physicists anticipated that the liberated quarks and gluons would behave like a gas, with particles moving independently and chaotically. Instead, the plasma flows collectively with a viscosity to entropy ratio that approaches the theoretical minimum allowed by quantum mechanics. This perfect liquid behavior suggests that even at temperatures where individual particles lose their identity, collective motion can still emerge. The implications extend far beyond particle physics. The study of quark-gluon plasma provides insights into the behavior of matter under the most extreme conditions imaginable, conditions that shaped the evolution of the early universe. By understanding how matter behaved in those first moments, scientists can better understand how the universe evolved from a hot, dense soup into the structured cosmos we see today, with galaxies, stars, planets, and ultimately life. Quark-gluon plasma is not the only high-energy state that challenges our understanding. Consider Rydberg matter, born not of heat but of excitation. In a Rydberg atom, an electron is pushed far from its nucleus, orbiting at great distances. The atom becomes bloated, inflated to sizes far larger than normal, yet still bound. When many such atoms gather, they can form clusters, strange, fragile states where matter is expanded, tenuous, and unstable. These clusters blur the line between the microscopic and the macroscopic, hinting at new ways matter can organize when its rules are stretched. Rydberg atoms represent matter in an extremely excited state, where electrons orbit their nuclei at distances that can be hundreds or even thousands of times larger than in ground state atoms. To put this in perspective, if a normal hydrogen atom was scaled up to the size of a football field, a Rydberg atom would be the size of a small country. These inflated atoms are incredibly fragile. The slightest disturbance can ionize them, yet they exhibit fascinating collective behavior when brought together. The formation of Rydberg matter occurs when these giant atoms interact through van der Waals forces, the same weak attractions that hold gas molecules together at low temperatures. But because Rydberg atoms are so large, these normally weak forces can become significant, allowing the atoms to form weakly bound clusters and even extended crystalline structures. The resulting material has a density that can be millions of times lower than ordinary matter, creating a state that is almost more empty space than substance. What makes Rydberg matter particularly intriguing is its potential connection to astrophysics. Some researchers have proposed that Rydberg matter might form naturally in the extremely low-density environments of interstellar space, where the usual mechanisms that would destroy such fragile states are absent. If true, vast clouds of Rydberg matter might drift between the stars, invisible and undetected, representing a form of matter we've barely begun to understand. Study of Rydberg atoms has also revealed new insights into the quantum world. Because the electron orbits are so large, Rydberg atoms are exquisitely sensitive to external electric and magnetic fields. This sensitivity makes them ideal for precision measurements and for studying the transition between quantum and classical behavior. In some sense, Rydberg atoms represent quantum mechanics scaled up to nearly macroscopic dimensions, allowing us to observe quantum effects that would normally be invisible. There are also states that arise not in colliders, but in the depths of stars. In the crushing gravity of a neutron star, protons and electrons are squeezed together, creating a sea of neutrons packed so densely that a single teaspoon would weigh billions of tons. Within this unimaginable density, neutrons themselves may form superfluids, and the interior of the star may host phases of matter we cannot yet replicate. Some theories even suggest quark matter at the core, where confinement finally breaks under the weight of gravity and quarks drift in a permanent plasma. If so, then neutron stars are not just celestial bodies, but laboratories holding exotic matter in their hearts. Neutron stars represent some of the most extreme laboratories in the universe, where matter is compressed to densities that exceed even the nuclei of atoms. When a massive star exhausts its nuclear fuel and can no longer support itself against gravitational collapse, its core implodes in one of the most violent events in the universe. The collapse is so rapid and complete that protons and electrons are crushed together to form neutrons, creating a city-sized object with the mass of the Sun. The conditions inside neutron stars are so extreme that our understanding of matter is pushed to its very limits. At the surface, the gravitational field is 200 billion times stronger than Earth's. The magnetic field can be 1 trillion times stronger than any magnet on Earth. The temperature can reach millions of degrees, yet the star's interior may contain superfluid neutrons flowing without friction and superconducting protons carrying endless electrical currents. The inner structure of neutron stars remains one of the greatest puzzles in astrophysics. As you journey toward the center, the density increases beyond anything we can replicate in terrestrial laboratories. The outer layers contain a solid crust of heavy nuclei arranged in a crystalline lattice. But deeper inside, as the pressure mounts, these nuclei begin to dissolve, releasing their neutrons into a superfluid sea. Even deeper, theories predict phases of matter that have no analog on Earth. Hyperons, particles containing strange quarks, might appear, creating a kind of exotic nuclear soup. At the very center, the pressure might be so intense that neutrons themselves dissolve, liberating their constituent quarks into a state similar to the quark-gluon plasma created in particle accelerators, but stable and permanent rather than fleeting. The study of neutron stars provides a unique window into fundamental physics under conditions that cannot be reproduced in any laboratory. When neutron stars merge, events that have been detected through gravitational waves, they create environments where we can observe the properties of ultra-dense matter in real time. These cosmic collisions serve as natural experiments revealing how matter behaves under the most extreme conditions in the universe. Recent observations have revealed that neutron stars can contain phases of matter that challenge our understanding of the strong nuclear force. Some neutron stars appear to be more compact than theory predicts, suggesting that matter at these densities might become softer than expected. Others seem to support masses that approach the theoretical maximum, indicating that exotic phases of matter might provide additional pressure to resist gravitational collapse. And then there are speculative states, ideas not yet confirmed but dreamed of by physicists exploring the frontier. Strange matter, composed of unusual combinations of quarks, might be more stable than ordinary matter under certain conditions. Color superconductors, phases where quarks pair in analogies to electron pairing, might exist in the depths of stars. These states are not fantasies, but hypotheses, grounded in equations awaiting either discovery or disproof. They remind us that the map of matter is not finished, that blank spaces remain where imagination can wander. Strange matter represents one of the most intriguing possibilities in theoretical physics. According to some theories, matter composed of roughly equal numbers of up, down, and strange quarks, known as strange quark matter, might actually be more stable than ordinary atomic matter. If this is true, it would mean that every atom in the universe is metastable, existing in a state that could, in principle, decay into something more fundamental. The implications are staggering. A single strange quark nugget, if it existed and if it came into contact with ordinary matter, could theoretically convert normal atoms into strange matter through a chain reaction. The entire planet could be transformed in an instant, though most physicists consider this scenario extremely unlikely given current understanding of quark confinement. Strange stars, hypothetical stellar objects composed entirely of strange quark matter, might exist alongside conventional neutron stars. These objects would be even more compact and could have properties that distinguish them from neutron stars. Some gamma-ray bursts and other high-energy astronomical phenomena might be signatures of strange star formation or interactions. Color superconductivity represents another frontier in exotic matter physics. Just as electrons in ordinary superconductors form Cooper pairs that carry electrical current without resistance, quarks at ultra-high density might form analogous pairs that carry color charge, the quantum number associated with the strong nuclear force without resistance. This state would be a superconductor not for electricity but for the strong force itself. The quarks would pair up in specific color combinations, creating energy gaps in the quark spectrum and fundamentally altering how the strong force operates at these densities. Different types of color superconducting phases are theoretically possible, each with its own symmetry breaking pattern and unique properties. The study of color superconductivity bridges particle physics and condensed matter physics in fascinating ways. The mathematical techniques developed to understand conventional superconductors find new applications in the realm of quark matter, while the extreme conditions of quark matter reveal new possibilities for quantum many-body physics. What unites all of these high-energy states is that they are glimpses into conditions far from human experience. We live at moderate temperatures and pressures, sheltered within a narrow band of possibility. But the universe itself spans extremes, from the near absolute zero of interstellar space to the unimaginable heat of stellar cores and the first moments of creation. Exotic matter exists at those edges, and by studying it, we bridge the gap between our world and the cosmos. But we've barely scratched the surface of what exotic matter can teach us about ourselves and our place in the cosmos. Let me tell you about some of the most mind-bending discoveries that are happening right now in laboratories around the world, states so strange they force us to question everything we thought we knew about reality itself. Scientists are currently working with something called topological insulators, materials that are insulators on the inside but conduct electricity on their surfaces with perfect efficiency. It's as if you had a house where the interior walls blocked all sound, but the outside walls carried whispers perfectly from one end to the other. These materials challenge our basic understanding of how electrons behave and could revolutionize electronics. The electrons on the surface move in protected channels, immune to disorder, as if they were following invisible highways that nothing can block. What makes this even more remarkable is that these surface states are guaranteed by the topology of the material itself, the mathematical structure that describes how the electron waves wind around in quantum space. The discovery of topological insulators has opened an entirely new field in condensed matter physics. Unlike conventional materials, where the distinction between insulators and conductors depends on the details of the electronic band structure, topological insulators are protected by deep mathematical principles that relate to the topology of the quantum wave functions. Imagine trying to turn a sphere inside out without tearing it. It's impossible because of the sphere's topological properties. Similarly, you cannot continuously deform the electronic structure of a topological insulator to make it an ordinary insulator without closing the energy gap and going through a phase transition. This topological protection ensures that the surface conducting states are robust against impurities, defects, and disorder that would normally destroy electronic conductivity. The surface electrons in topological insulators have another remarkable property. They are helical, meaning their spin is locked perpendicular to their direction of motion. This creates a direct connection between the electron's motion and its quantum spin, a property that could be exploited for spintronics applications where information is stored and processed using electron spin rather than just charge. Then there are time crystals, structures that repeat not in space but in time. Imagine a clock that ticks forever without any energy source, its pattern repeating endlessly through the fourth dimension. These were once thought to be impossible, violating fundamental laws of physics until they were created in the lab in 2006. They represent a new phase of matter that exists outside our normal understanding of equilibrium. In a time crystal, atoms oscillate between different configurations in a regular pattern that continues indefinitely, like a perpetual motion machine of quantum states. They break time translation symmetry, meaning they look different at different moments, yet they do so in a perfectly predictable, periodic way. The concept of time crystals emerged from theoretical work by Nobel laureate Frank Wilczek, who asked whether it was possible to have crystals in time just as we have crystals in space. Regular crystals break spatial translation symmetry. They look different when you move from one location to another due to the regular arrangement of atoms. Wilczek wondered if there could be systems that break time translation symmetry, looking different at different times while still maintaining some underlying periodicity. The first experimental realizations of time crystals used trapped ions or nitrogen vacancy centers in diamond, systems where quantum spins could be manipulated with exquisite precision. By driving these systems with periodic external fields, researchers found that the spins would respond with a period different from the driving frequency, typically twice as long. This period doubling is the signature of time crystalline behavior, where the system spontaneously chooses its own temporal rhythm that differs from the external driving. What makes time crystals truly remarkable is that they exist in a state of non-equilibrium, steady state. Unlike ordinary crystals, which are in thermal equilibrium with their environment, time crystals are constantly absorbing and dissipating energy while maintaining their temporal structure. They represent a new class of many-body quantum systems that can exhibit coherent, periodic behavior indefinitely without reaching thermal equilibrium. There are also quantum spin liquids, where magnetic moments never settle into a fixed pattern but remain in constant fluid motion even at absolute zero. It's like having a dance where the dancers never stop moving, never fall into a rhythm, but maintain perfect choreography in their chaos. These states could be the key to new forms of quantum computing that are naturally protected from the errors that plague current quantum devices. The spins in these materials are entangled in such complex ways that they form a quantum web where information is spread out and protected, impossible to destroy by local perturbations. Quantum spin liquids represent one of the most exotic phases of matter, where quantum entanglement prevents the system from settling into any ordered pattern even at absolute zero temperature. In a conventional magnet, spins align in regular patterns, all pointing in the same direction in a ferromagnet or alternating in an antiferromagnet. But in a quantum spin liquid, the spins remain in constant quantum motion, locked in a highly entangled state that resists any form of magnetic ordering. The theoretical framework for understanding spin liquids involves concepts from topology and quantum field theory. These systems can support exotic excitations called anyons, particles that are neither bosons nor fermions but something in between. When anyons are exchanged, they pick up quantum phases that depend on their braiding paths, creating a kind of topological memory that could be used for fault-tolerant quantum computing. The search for spin liquid materials has led to the discovery of several candidate compounds, including certain organic salts and frustrated magnetic systems where competing interactions prevent conventional magnetic ordering. These materials exhibit unusual properties such as linear specific heat and persistent magnetic fluctuations down to the lowest temperatures, signatures of the underlying quantum entanglement. Recent experiments have also revealed matter waves, not individual particles behaving like waves, but entire substances taking on wave-like properties at macroscopic scales. Researchers have created matter interferometers where clouds of atoms split, travel different paths, and then recombine, creating interference patterns visible to the naked eye. It's as if reality itself is waving at us, showing us that the wave-particle duality extends far beyond individual atoms. These experiments push the boundaries of where quantum mechanics ends and classical physics begins, revealing that the quantum world can reach up into our everyday scale under the right conditions. Consider also the phenomenon of many-body localization, where quantum systems can remember their initial conditions forever, never reaching thermal equilibrium. It's like having a cup of coffee that never cools down, maintaining pockets of hot and cold indefinitely. This challenges our understanding of how complex systems evolve and could lead to new ways of storing quantum information. In a many-body localized system, the normal rules of thermodynamics break down. Information becomes frozen in place, trapped by the complex interactions between particles. This creates a kind of quantum glass where the system remains forever out of equilibrium, preserving the memory of its past. Many-body localization represents a fundamental breakdown of the assumptions underlying statistical mechanics and thermodynamics. In normal materials, interactions between particles lead to thermalization. The system eventually reaches thermal equilibrium where all memory of initial conditions is lost. But in strongly disordered systems with the right kind of interactions, localization can prevent thermalization indefinitely. This phenomenon has profound implications for quantum information. In a many-body localized system, quantum information encoded in the initial state can be preserved indefinitely, protected by the localization of the constituent particles. This could lead to new forms of quantum memory that don't require active error correction, storing information in the stable, non-thermal phases of strongly interacting quantum systems. There are metamaterials with negative refractive indices that bend light backwards, potentially leading to invisibility cloaks. These artificial structures are engineered at scales smaller than the wavelength of light, creating materials with properties that don't exist in nature. They can make objects invisible by guiding light around them as if the object weren't there at all. But the implications go beyond invisibility. These materials reveal that the electromagnetic properties we take for granted, how light bends, reflects, and absorbs, are not fundamental but can be engineered at will. Metamaterials represent a revolution in materials science, where properties are determined not by chemical composition but by structure. By arranging ordinary materials in carefully designed patterns at scales smaller than the wavelength of the phenomenon you want to control, you can create effective properties that seem to violate common sense. Negative index metamaterials can make light behave as if it's traveling backwards, enabling perfect lenses that can focus light beyond the diffraction limit. This could revolutionize microscopy, allowing us to see details smaller than the wavelength of light itself. Such superlenses could enable optical lithography with unprecedented resolution, leading to electronic devices with features smaller than anything possible with conventional optics. The concept extends beyond optics into other areas of physics. Acoustic metamaterials can control sound waves in similar ways, creating materials that can cloak objects from sonar or focus sound with incredible precision. Mechanical metamaterials can have properties like negative Poisson's ratio, becoming thicker when stretched rather than thinner. Thermal metamaterials can control heat flow, potentially leading to thermal cloaking devices or materials with programmable thermal properties. There are phononic crystals that control sound waves the way semiconductors control electrons. These materials can create acoustic metamaterials that make sounds invisible, bend them around corners, or focus them with incredible precision. Imagine being able to manipulate sound as easily as we manipulate light, creating acoustic lenses, mirrors, and even acoustic computers that process information through sound waves rather than electrons. There are materials with programmable properties that can change their behavior on command. Shape memory alloys remember previous forms and return to them when heated. Programmable matter could one day assemble itself into any desired configuration, transforming from a flat sheet into a complex three-dimensional structure with just a signal. This points toward a future where materials are not static but dynamic, able to adapt and reconfigure themselves based on need. The vision of programmable matter extends to the molecular level, where scientists are developing materials that can be reconfigured at will. DNA origami techniques allow researchers to fold DNA strands into precise three-dimensional shapes, creating molecular machines that can change configuration in response to chemical signals. These biological materials bridge the gap between living and non-living matter, suggesting new possibilities for materials that can grow, adapt, and even reproduce. Scientists are exploring liquid crystal phases of DNA, where the molecules of life itself can form exotic states of order. DNA, the blueprint of life, can organize into liquid crystals under certain conditions, creating materials that are both biological and technological. These states bridge the gap between living and non-living matter, suggesting that the principles governing life and the principles governing exotic matter are not as different as we once thought. They're investigating active matter, materials that consume energy and move on their own, blurring the line between living and non-living. Flocks of birds, schools of fish, and even crowds of people can be understood as active matter systems with their own phase transitions. These systems can organize spontaneously, creating patterns and behaviors that emerge from the collective motion of individual components. Active matter reveals that organization and lifelike behavior don't require life itself. They can emerge from purely physical processes. Active matter represents a new frontier in understanding how order emerges from disorder. Unlike equilibrium systems, active matter systems are constantly consuming energy and converting it to motion, creating flows and patterns that can appear remarkably lifelike. Bacterial colonies, cell tissues, and even synthetic systems like self-propelled particles can exhibit collective behavior that includes flocking, swarming, and the formation of complex patterns. These systems undergo their own phase transitions, changing from disordered motion to collective flow as the density or activity of the particles is varied. The mathematics describing these transitions has connections to both fluid dynamics and statistical mechanics, revealing universal principles that govern the emergence of collective motion across vastly different scales. In the realm of artificial matter, researchers are creating optical lattices, grids of light that can trap atoms and force them to behave like electrons in materials that don't exist in nature. These quantum simulators allow us to explore theoretical phases of matter, testing ideas that might exist in other worlds or under conditions we can never naturally achieve. By arranging atoms in artificial crystals made of light, scientists can study exotic phases of matter that might exist in the cores of neutron stars or in the first moments after the Big Bang. There's even something called matter out of light. Experiments where photons, particles of light that normally have no mass, are made to behave like matter. Using strong magnetic fields and intense laser pulses, scientists can create states where light becomes viscous, where photons interact and flow like a liquid. It's the closest we can come to turning pure energy into tangible substance. These photonic fluids can form their own vortices, waves, and even crystalline structures, showing that the distinction between matter and energy is not as absolute as we once believed. The frontiers extend into biological systems too. Living cells can exist in glass-like states where all molecular motion stops, but life persists. Seeds can remain dormant for thousands of years, existing in a state that's neither fully alive nor dead. Some organisms can enter cryptobiosis, a state of suspended animation where metabolism stops entirely but can be restarted. These biological exotic states suggest that life itself might be far more flexible and resilient than we imagine, able to exist in forms that challenge our definitions of what it means to be alive. What about quantum biology? There's growing evidence that quantum effects play crucial roles in photosynthesis, bird navigation, and possibly even consciousness itself. Plants might use quantum superposition to find the most efficient path for energy transfer, exploring all possible routes simultaneously until they find the optimal one. Birds might navigate using quantum entanglement in their retinas, where pairs of particles maintain mysterious connections that allow them to sense magnetic fields with extraordinary precision. If consciousness involves quantum processes, then our minds might be operating in exotic states we don't yet understand, processing information through quantum coherence and entanglement. The discovery of quantum effects in biological systems has revolutionized our understanding of life itself. Photosynthesis, the process that powers virtually all life on Earth, appears to use quantum coherence to achieve near-perfect efficiency in energy transfer. When sunlight hits a photosynthetic complex, the energy doesn't simply bounce randomly from molecule to molecule until it reaches the reaction center. Instead, quantum superposition allows the energy to explore multiple pathways simultaneously, finding the most efficient route through quantum interference. This quantum coherence persists even in the warm, noisy environment of living cells, where it was thought impossible for quantum effects to survive. The discovery suggests that evolution has learned to harness quantum mechanics, creating biological structures that protect and exploit quantum coherence for enhanced performance. Bird navigation presents another stunning example of quantum biology. Many migrating birds can sense Earth's magnetic field with extraordinary precision, navigating thousands of miles with remarkable accuracy. Recent research suggests this magnetic sense might rely on quantum entanglement between pairs of electrons in specialized proteins in the bird's retina. When these entangled electrons are exposed to magnetic fields, their quantum states change in ways that could provide directional information to the bird's nervous system. Even more speculative is the possibility that consciousness itself might have quantum origins. Some theories suggest that quantum processes in microtubules within brain cells could give rise to consciousness, allowing the brain to process information in ways that classical computers cannot. While highly controversial, these ideas point to the possibility that our minds might be operating as biological quantum devices, processing information through quantum superposition and entanglement. The search for room temperature superconductors continues to surprise us. Recent discoveries of superconductivity in materials as simple as graphene layers twisted at specific angles suggest that exotic quantum states might be hiding everywhere, waiting to be unlocked by the right conditions. These magic angle graphenes reveal that superconductivity might be far more common than we thought, hidden in plain sight in materials we use every day. If we could achieve superconductivity at everyday temperatures, it wouldn't just change technology, it would transform our relationship with energy itself. The discovery of superconductivity in twisted bilayer graphene has opened an entirely new field of research called twistronics. By rotating one layer of graphene relative to another by a precise magic angle of about 1.1 degrees, the electronic properties of the system are dramatically altered. The resulting moire pattern creates a new periodic structure that can trap electrons and modify their interactions in profound ways. At the magic angle, the electronic bands become extremely flat, meaning electrons move very slowly and interact strongly with each other. This creates conditions where novel correlated states can emerge, including superconductivity, correlated insulators, and exotic magnetic phases. The system becomes a playground for exploring strong correlation effects that are usually associated with much more complex materials. The implications extend far beyond graphene. The principle of using geometric frustration and moire patterns to engineer electronic properties could be applied to many other two-dimensional materials. By stacking different materials at controlled angles, researchers might be able to design quantum materials with precisely tailored properties, opening the door to a new era of quantum engineering. And here's something that will make you question everything. Some physicists propose that space and time themselves might be exotic states of some more fundamental substance. Just as water can exist as ice, liquid, or vapor, perhaps space-time can exist in different phases. The Big Bang might have been a phase transition, the formation of black holes might be another, and what we call empty space might be just one possible state of a deeper reality. This suggests that the very fabric of the universe could transform into something entirely different under extreme conditions, revealing that even space and time are not fundamental but emergent properties of something more basic. The idea that space-time itself might be an emergent phenomenon represents one of the most radical proposals in modern physics. According to some theories, what we perceive as continuous space and time might actually emerge from more fundamental, discrete building blocks, much like how the smooth surface of a liquid emerges from the chaotic motion of individual molecules. String theory and loop quantum gravity both suggest that at the smallest scales, the Planck scale, about 10 35 meters, space and time lose their continuous nature and become grainy, made up of discrete units. At these scales, the familiar concepts of distance and duration might break down entirely, replaced by more fundamental quantum relationships. Some theories propose that space-time emerges from quantum entanglement. In this view, the connections we perceive as spatial relationships are actually manifestations of quantum correlations between more fundamental degrees of freedom. When quantum systems become entangled, they create the geometric relationships we interpret as space. Time, in this framework, emerges from the dynamics of these quantum correlations. The implications are staggering. If space-time is indeed an emergent phenomenon, then under extreme conditions, perhaps in black holes or during the Big Bang, it might undergo phase transitions into forms we cannot currently imagine. Just as water can transition from liquid to gas to plasma, space-time might transform into states that bear no resemblance to our everyday experience of reality. Consider the possibility that our entire universe is just one bubble in an infinite ocean of cosmic foam, each bubble representing a different phase of existence with its own laws of physics. In some bubbles, matter might be completely exotic by our standards. In others, the very concepts of matter and energy might not apply. The constants we take for granted, the speed of light, the strength of gravity, the charge of an electron might be variable, changing from one cosmic phase to another. Even what we call empty space turns out to be far from empty. The quantum vacuum seethes with virtual particles that pop in and out of existence, creating a background energy that permeates the entire universe. This vacuum energy has measurable effects. It shifts the energy levels of atoms in tiny but detectable ways, and it might be responsible for the mysterious dark energy that's accelerating the expansion of the universe. The quantum vacuum represents one of the most counterintuitive aspects of modern physics. According to quantum field theory, even completely empty space, a perfect vacuum with no matter or radiation, still contains quantum fields that are constantly fluctuating. These fluctuations give rise to virtual particle pairs that briefly emerge from the vacuum before annihilating each other and disappearing back into nothingness. The Casimir effect provides a direct demonstration of these vacuum fluctuations. When two uncharged metal plates are placed very close together in a vacuum, they experience a tiny attractive force. This force arises because the quantum fluctuations of the electromagnetic field are restricted between the plates, creating a pressure difference that pushes the plates together. It's as if the emptiness between the plates is different from the emptiness outside them. The implications of vacuum energy extend to cosmology. Some theories suggest that the energy of the quantum vacuum could be the source of dark energy, the mysterious force that's causing the universe to accelerate its expansion. If true, This would mean that the fate of the cosmos is determined by the quantum properties of empty space itself. The ability to create artificial quantum systems has opened unprecedented opportunities for exploring exotic states of matter. Cold atom systems in optical lattices can simulate materials that don't exist in nature, allowing scientists to test theoretical predictions about exotic phases of matter. These quantum simulators can explore parameter regimes that are impossible to reach in natural materials, revealing new physics that bridges the gap between condensed matter and high-energy physics. Trapped ion systems provide another platform for creating exotic quantum states. By precisely controlling the motion and internal states of individual ions, researchers can create quantum spin models that exhibit topological order, anyonic excitations, and other exotic phenomena. These systems allow for the creation of quantum states that are both well-controlled and highly entangled, providing testbeds for theories of quantum many-body physics. Superconducting circuits have emerged as powerful tools for quantum simulation and computation. These macroscopic quantum systems can be engineered with extraordinary precision, allowing researchers to create artificial atoms, molecules, and even more complex quantum structures. The ability to design the interactions between these artificial quantum systems from first principles provides unprecedented control over quantum many-body phenomena. The development of quantum computers is intimately connected to our understanding of exotic states of matter. Topological quantum computers would rely on anyonic excitations in topological superconductors, exotic quasi-particles that emerge in certain strongly correlated electron systems. These anyons have the remarkable property that braiding them around each other performs quantum computations that are naturally protected from errors. The search for topological superconductors has led to the discovery of Majorana fermions, particles that are their own antiparticles. These exotic excitations, first predicted by Italian physicist Ettore Majorana in 1937, have finally been observed in carefully engineered semiconductor-superconductor heterostructures. Majorana fermions could form the basis of topological qubits, quantum bits that are inherently protected from the environmental noise that plagues conventional quantum computers. Quantum error correction represents another frontier where exotic states of matter meet quantum information. Certain phases of matter can naturally encode quantum information in non-local degrees of freedom that are protected from local perturbations. These topologically ordered states could provide the foundation for fault-tolerant quantum computing, where quantum information is stored in the global properties of many-body quantum systems. The ability to engineer materials with specific quantum properties has launched a new era of materials science. By controlling the arrangement of atoms and molecules with atomic precision, scientists can create materials with properties that were once thought impossible. Topological insulators, Weyl semimetals, and quantum spin liquids are just the beginning of what might be possible with designer quantum materials. Machine learning and artificial intelligence are accelerating the discovery of new exotic materials. By training algorithms to recognize patterns in the electronic structure of materials, researchers can predict which combinations of elements might exhibit superconductivity, topological order, or other exotic properties. This computational approach is revolutionizing materials discovery, allowing scientists to explore vast spaces of possible materials that would take centuries to investigate experimentally. The development of new synthesis techniques is also pushing the boundaries of what materials can be created. Molecular beam epitaxy allows for the growth of materials with atomic layer precision, creating interfaces and heterostructures with properties that emerge solely from their carefully engineered geometry. Chemical vapor deposition and other advanced techniques enable the creation of materials with precisely controlled defects, dopants, and structural modifications. The discovery of exotic states of matter is intimately connected to our search for new physics beyond the standard model. Axion insulators predicted to arise from the hypothetical axion particle that might solve the strong CP problem in particle physics could exhibit electromagnetic properties that violate parity and time reversal symmetry. The search for these materials represents a bridge between condensed matter physics and fundamental particle physics. Dark matter interactions could manifest in exotic phases of ordinary matter. If dark matter particles interact weakly with normal matter, they might influence the formation of novel quantum phases or create topological defects that could be detected in sensitive experiments. Some theories suggest that dark matter could form its own exotic states, dark atoms, dark molecules, or even dark crystals, existing in parallel to our visible universe. Extra dimensions, if they exist, might manifest their effects through exotic matter phases. Theories with compact extra dimensions predict new particles and interactions that could dramatically modify the behavior of matter under extreme conditions. These effects might be most visible in exotic quantum phases, where the normal rules of three-dimensional physics are modified by the presence of additional spatial dimensions. The connection between exotic quantum states and biological systems continues to surprise researchers. Beyond the well-established examples of quantum coherence in photosynthesis and bird navigation, new discoveries are revealing quantum effects in other biological processes. Enzyme catalysis, the process that drives most biochemical reactions, might exploit quantum tunneling to achieve reaction rates that would be impossible through classical mechanisms alone. The sense of smell might rely on quantum vibrations of molecules rather than just their shapes. This vibrational theory of olfaction suggests that the nose can detect the quantum vibrations of odorant molecules, providing a mechanism for the extraordinary sensitivity and selectivity of the olfactory system. If true, it would mean that our sense of smell is actually a quantum sensor capable of detecting molecular vibrations. DNA damage and repair mechanisms might involve quantum coherence effects that help maintain the integrity of genetic information. Some researchers have proposed that quantum error correction mechanisms, similar to those being developed for quantum computers, might naturally occur in biological systems to protect genetic information from damage. Perhaps the most speculative but fascinating frontier is the possible connection between exotic quantum states and consciousness itself. While the idea that consciousness arises from quantum effects in the brain remains highly controversial, new discoveries about quantum biology and the behavior of microtubules in neurons are providing fresh perspectives on this ancient question. If consciousness does involve quantum processes, then the human brain might be operating as a biological quantum computer, processing information through quantum superposition, entanglement, and coherence. This could explain some of the mysterious properties of consciousness, such as the binding problem, how the brain integrates diverse sensory inputs into a unified conscious experience. The implications would be profound. It would mean that consciousness is not just an emergent property of classical neural networks, but a manifestation of quantum many-body physics. The same principles that govern exotic states of matter might also govern the most intimate aspects of human experience. As our ability to control and manipulate exotic states of matter advances, we may be approaching a kind of technological singularity in materials science, a point where our control over matter becomes so precise and comprehensive that we can create virtually any material we can imagine. Programmable matter that can reconfigure itself at will, materials that can repair themselves and adapt to changing conditions, and substances that blur the line between living and non-living matter are all within the realm of possibility. We might develop materials that can think, feel, and respond to their environment in ways that challenge our fundamental categories of matter and life. The convergence of artificial intelligence, quantum computing, and exotic matter could lead to materials that are not just programmable but intelligent, substances that can learn, adapt, and evolve on their own. These smart materials could revolutionize every aspect of technology, from architecture that grows and adapts to its inhabitants to spacecraft that can repair and reconfigure themselves during long interstellar journeys. The discovery of exotic states of matter forces us to confront fundamental questions about the nature of reality itself. If matter can exist in states where individual particles lose their identity and merge into collective quantum entities, what does this tell us about the nature of individuality and identity? If consciousness might be a quantum phenomenon, what does this mean for our understanding of free will and the relationship between mind and matter? The ability of matter to exist in phases that seem to violate our everyday understanding of physics, where electricity flows without resistance, where liquids flow without friction, where particles can be in multiple places at once, suggests that reality is far stranger and more flexible than our intuitions suggest. we are forced to confront the possibility that the familiar world of solid objects and predictable behavior is just a narrow slice of a much richer and more mysterious universe. These discoveries also raise profound questions about the relationship between observer and observed. In quantum mechanics, the act of measurement plays a fundamental role in determining the properties of a system. In exotic quantum states where the boundaries between individual particles become blurred, the role of the observer becomes even more mysterious and central. As we stand at this moment in history, surrounded by the exotic states of matter we've created and discovered, we are witness to a transformation in our understanding of reality that rivals the greatest scientific revolutions of the past. We have learned that matter is not fixed but fluid, not limited but infinitely creative, not separate from consciousness but possibly intimately connected to it. The implications stretch far into the future of human civilization. As we learn to control these exotic states, we might develop technologies that seem like magic today. Imagine materials that repair themselves, growing stronger when damaged, adapting to their environment like living tissue. Computers that run on the quantum properties of consciousness, processing information through direct manipulation of quantum states. Energy systems that tap directly into the fabric of space-time, drawing power from the vacuum itself. We might even develop ways to alter the fundamental constants of nature in localized regions, creating pockets where the laws of physics are different. This could lead to new forms of space travel where we create bubbles of altered space-time that allow faster-than-light motion. We might learn to create pocket universes with their own physical laws, serving as laboratories for testing the fundamental nature of reality. But perhaps the most profound realization is that we are still at the very beginning of this journey. Every exotic state we discover opens up new questions, new possibilities, new horizons to explore. The universe continues to surprise us with its creativity, revealing new ways for matter to organize itself, new forms of order and beauty that we never imagined possible. We live in a cosmos where solid matter can become perfectly fluid, where light can be stopped and stored, where empty space seethes with energy, and where consciousness itself might be a quantum phenomenon. We inhabit a reality so rich and strange that most of it remains hidden from our everyday experience, waiting to be discovered by those bold enough to push the boundaries of the possible. The story of exotic matter is really the story of human curiosity itself, our endless drive to understand, to explore, to push beyond the familiar into the unknown. It is a testament to the power of imagination, guided by rigorous observation, of theoretical vision tested by careful experiment. It reminds us that the universe is not a finished book, but a story still being written, with each new discovery adding another chapter to the grand narrative of existence. As we continue this journey into the exotic realms of matter, we carry with us the wisdom of all those who came before, the ancient philosophers who first imagined atoms, the medieval alchemists who dreamed of transformation, the modern physicists who unlocked the secrets of the quantum world. We are the latest chapter in humanity's oldest quest to understand the nature of reality itself. And in that quest, exotic matter is not just a subject of study, but a mirror, reflecting back to us the infinite creativity of the universe and our own limitless capacity for wonder and discovery. In every Bose, Einstein condensate that forms in our laboratories, in every superconducting loop that carries endless current, in every quantum spin liquid that defies conventional order, we see reflected the same principles that shape the cosmos itself. The tendency toward unity, the power of collective behavior, the emergence of order from apparent chaos. The dance of discovery continues, and we are both observers and participants in this cosmic ballet. Each experiment we design, each theory we propose, each exotic state we create adds another step to this eternal choreography of understanding. We are not separate from the universe we study, but part of it, conscious beings made of quantum matter investigating the quantum nature of reality. In the end, exotic states of matter teach us that existence itself is far more exotic than we ever imagined. They show us a universe that is not mechanical, but magical, not predictable, but surprising, not limited, but infinite in its possibilities. They remind us that we live in a reality where the impossible becomes possible, where the unimaginable becomes real, and where wonder never ends. As you go about your daily life, remember that you are made of the same quantum fields that create Bose. Einstein condensates that the atoms in your body once drifted freely as quark-gluon plasma in the early universe, that the very consciousness reading these words might itself be an exotic quantum phenomenon. You are not just an observer of exotic matter, you are exotic matter, organized into the most complex and beautiful pattern we know, a conscious being capable of understanding its own quantum nature. The universe is not done surprising us. The exotic states we know today will seem simple compared to what we might discover tomorrow. New phases of matter, new forms of quantum organization, new connections between mind and matter await discovery. The horizon of possibility stretches infinitely ahead, inviting us to continue the eternal human journey toward understanding. And that perhaps is the most exotic and wonderful discovery of all, that in a universe of infinite possibilities, wonder itself is infinite, and the dance of discovery will never end.